Hello, everybody. Hope that you're doing well today. Today's going to be a great stream. We are bringing back one of our favorite guests, the bad boy of science from the United Kingdom. So
Hello.
Go ahead and introduce yourself. Tell us who you are, and this will be a perfect opportunity for people to tell us if the levels are right, if we're all equally loud.
Sounds good. My name's Sam Gregson. I'm a Doctor of Particle Physics, formerly from the University of Cambridge over here in the UK, and the Large Hadron Collider where I worked on CP violations. CP violation, excuse me. So the differences between matter and antimatter. So today is we both had a quick look through all of the Nobel Prizes from the beginning of the 1900s up to date. And we've tried to condense them down into what we think are some of the most important ones from a scientific perspective.
And they're all in physics because that's the only science that really matters in the end.
Oh, there you go. Right. It's the only, it's the lowest level.
I'll say it out loud. Chemistry
is just the physics of the outer electron, and then biology is just physics of squishy stuff, right? It's, they're all subsets of physics.
And stuff that smells.
Exactly. Right. Squishy and smelly. So it's a slightly loose list. Obviously, there's a lot of room for debate on these things. But I thought I've got 10 that I think are pretty important in terms of the development of science, and some that are very important in just general society, and some for the wonder of science, some for the sort of technological leaps that they brought. So I'm interested to see if your lists sort of overlap with mine, and the ones that the viewers think are the most important as well. There's no right or wrong answers, I guess. It's just interesting to look at some of these milestones in history, and everyone loves a good rank, right? I think you were playing around, weren't you, with the
I tried to do a tier list thing,
where you tier list them, drag them on. People love that sort of stuff, so it's worth doing with Nobel Prizes.
All right, so here's what I propose. I thought about this long and hard for about 10 minutes today. And I propose that we start with the society list. So this is the top 10 physics Nobel Prizes for society.
So to be fair, you're better at the sort of historical implications of these things. Mine is very much lecturer in lecture series pointed this out, and therefore it's probably important. So, I know some about the history and how these link together, and you can see clear patterns in the giving of these prizes, right? So during the mid 19th century is where particle physics really explodes, and you can see the pattern of Nobel Prizes given for particle physics. Before that, you can see the Nobel Prizes that led up to special relativity, and then you can see the ones that were the foundations of quantum physics, and then later, your field, current field anyway, of astronomy starts to sort of creep back in as we move into the 2000s. So there's sort of these blocks of when certain subjects are more fashionable and when they're sort of having their heyday, I guess.
Right. All right, your list is ready to go.
Okay. You don't know my list, right?
I do not know your list.
Right.
Okay, so
I'm gonna start you off. I'll start with the earliest one I took out of there. I'm going to go for, I don't know if you can bring these up on the screen so people can see.
Yeah, so I'm gonna compile a list with your answers and then and my answers next to it.
And we're going to fight. Okay, yeah, I'm going to go for 1909, Marconi and Braun.
Okay, hold on 1 second. I do need to shift this over one row so that I can put your guesses and the correct answers side by side.
The correct answer.
Okay, so number 10 is Marconi.
I'm going to go, so I haven't actually put them in particular order, but I'm going to go Marconi and Braun.
So save your best one at least for last, so we'll put those.
Okay, what do I think is the most? Okay, I've got it. I've got which one I like.
Okay.
Between two, actually.
Okay, that's fine. You can flip a coin when we get to that part.
Yes, all right, fair enough. I'm gonna start with Marconi and Braun. In 1909
for radio transmission.
For radio transmission,
all right.
Because this is a discovery or a field of physics, I guess, which they were involved in that really opened up the world. Right, you've suddenly taken a world that is essentially huge, and with the speed of light, reduced it hugely. Right, so you've got communication over vast distances at very, very rapid speeds. And I think that's a very important move forward for society. Obviously, they're not the only people who are involved with it, but I think the general gist and the thrust of that Nobel Prize is an incredibly important leap forward.
Okay. So I had that one at number 2.
You had that one at number 2?
Yeah.
Okay, fine. Right. So I'm not going to argue with you too much about that. I think it's very important.
Yeah. Very cool. Okay. So number 9, or one of the ones that's tied for number 3. So
what, you want more? You want more from me?
No. So okay. So that was radio, and I have that one at number 2. I agree that like that really opened up what you could do in society. And there's a book. There's a book about a guy. So it was the first time that they used radio to catch someone. Like they were sailing across the Atlantic, and they were sending transmissions to the ship because there was a murderer on the ship. He was from the UK, so he and his mistress he had just murdered his wife, and he and the mistress were leaving the UK going to Canada, and they started communicating by radio that, oh, we think this is the person who's on the ship. And then when they arrived in Canada, they arrested him upon the spot.
It's amazing to think, like, just, I mean, you think now how we can't do anything without Zoom or mobile phones and stuff. Mm-hmm. To have to, send someone on a horse or something.
Pony Express, man, that was the way to go.
Crazy, like how much that opened up the world and made things so much easier and faster.
Yeah, the Pony Express was the BlackBerry of the 1870s.
Exactly.
So, and it lasted just about as long. Okay, number 9, or tied for number 3. Another element from tied for number 3. Another prize for you.
You want another one from me?
Yeah.
Okay. So you don't want the best.
No, so we're going from worst to like 10 to 1.
Okay, fine. So I'm going to go with on that same theme then. So when you say for society, do you mean like the technological advancements, or do you mean how it makes people think about themselves and think about their place in society? Because I've put on the one of Kellogg for the exoplanets, because I think this was a prize that really makes people feel small and think about their place in society. So I decided to put that one on,
even
though it's a very recent one.
So I was thinking more along like the technology advancement, but that's okay.
Okay.
So we'll put that there. I don't have that one on my list, so
right.
That's your first wrong answer. But okay, so what was the so what was it about the discovery of exoplanets?
It was a loose brief, right? So I blame it on that. The next technological one.
No. So what was it about the discovery of exoplanets that you think was so meaningful?
So I just feel that there's been a shift in the Nobel Prizes given recently, and maybe people will say that this is because there hasn't been the big landmark jumps forward, to more sort of prizes that make people think about the place of humans in the universe, for example. So the exoplanets one is a perfect example, right? And I think it's one of those ones that has deep resonance with people. Mm-hmm. When you can think of we are one amongst many. There are many Earths out.
Oh, your mic cut out again.
Oh, it cut out.
Okay, now you're back. You're back.
And that we might not be as special as we maybe thought we were. So I think it's something that gets people really interested in science. It inspires a sense of awe, and that's why I thought it maybe deserved a place on the list. Because
in society, yep. Kind of like first contact, right? It's the 0th contact.
And I think with that prize, you'll know a bit more about it than I will. But I think it was when was the first exoplanet discovered? Because this feels again like one of those prizes that has sort of been hanging around and didn't really get a prize at the time when it was discovered.
So
and then as
they kind of depends
the field
on...
has sort of expanded and exploded, now it feels like there's recognition worthy in society for that prize.
Yeah.
Seems like the time is right for it.
It depends on what you mean by the first discovery. So the first official discovery, I think, was 1988 or 1989 with the pulsar planets. And then the first ones discovered around a main sequence star were actually a little bit earlier in the 90s, but they weren't recognized as planets until after the ones that actually won the Nobel Prize, and that was in 1995. So 1995 is pretty universally recognized as the watershed moment where exoplanets were discovered, and then there's also a recognition that there were certainly hints and other signals that had been discovered before then that have since been counted as exoplanets. As an exoplanet discovery. Okay, number 8 for you.
And if you want me to go with more technologically based, I know you've got a big bee in your bonnet about 2014.
Okay.
Which is the blue LEDs. So if you want to lead on that one and explain why it's so important, because you've given me a big lecture before on why this is so important.
All right, so you have.
I decided it had to be on the list, otherwise you'd kill me.
Yeah. Okay, so the blue LED, you have it at 8. I have it at 7.
Okay, good. So we'll give that a right answer. Can I have a tick for that?
Yeah, you get that one. Okay, right. So the reason the blue LED is important is because LEDs consume considerably less energy. So with incandescent light bulbs, you emit light at all wavelengths, and it's only the fraction of the light that gets emitted that's in the visible part of the spectrum, and so the rest of that is energy that just...
Well, not all wavelengths, but over a continuous spectrum, because otherwise you'd be emitting hard X-rays and such. But I know what you mean.
Yeah, well, I mean, so to the extent that it is modelable with black body radiation, then you do get some hard X-rays. It's just that they're incredibly rare, right? You have to wait around for the age of the universe. I think your sound went back out again. Okay, now it's back.
Okay.
Whatever, like maybe you turn your head slightly to the side, then all of a sudden the sound goes out or something.
I'm just going to I'm just not going to
stay perfectly still. Okay, so and so you throw away all this energy that is in the infrared and the ultraviolet part of the spectrum, and it's the majority of the energy for incandescent light bulbs. So then you do better at energy efficiency, the efficiency of converting energy into visible light with fluorescent light bulbs, but that's still not the best. And then with LEDs, all of the light coming from LEDs is in a narrow band. So those, you would be able to do LED lights, or we couldn't do LED lights because there wasn't a blue LED in the past. And so we wouldn't be able to do LED lighting until there was a way to produce white light from it, where you have light coming from the blue, red, and the green parts of the spectrum. And so there had been green and red LEDs for a long time, but it was the invention of the blue LED that made it so that now you can produce white light with LEDs, and we can transition from incandescent light bulbs to LED light bulbs. And
without looking like we're in a red light district,
right? Exactly.
Window in the Netherlands or something.
So the blue LED, I thought that was a pretty important one. You have it. We're assigning it number 8 for you, and I have it at number 7.
Okay. Fine. So we're happy. I get a tick.
All right. Next.
Then I've gone with. So let's have a look at the ones that I've got that are tech based. I've gone with 2000.
Okay.
So. The name of the winner has slipped off, actually, for basic work on information and comms tech, which kind of goes in with the Marconi Prize. I'll just have to look up. For some reason, I didn't, when I did the copy paste, it slipped off. The 2000 Physics Nobel Prize went to Alferoz, Kromer, and Kilby. Mm-hmm. For their basic work on information and communication technology, and for developing semiconductor heterostructures in high speed and optoelectronics. Okay. So the new upgrade of Marconi, I guess, for the modern world. So,
all right, fair enough.
When we're talking about semiconductors, we're talking about computers, and when we're talking about computers, we're talking about everything that essentially underpins our modern world. So, I thought, in that spirit, it deserved a place on the technology list.
All right, very good. I don't have that one, partly because I didn't understand what it was. So,
so I will say we didn't have a perfect look into all of these, I don't think. Mm-hmm. But when we're talking about the general thrust of the prize, I think that's fair game.
Yep.
You don't have to know exactly the tiny thing, because there's obviously a lot of people working in that field on semiconductors and how semiconductors are used in devices. It's not just one single person who brought that advancement forward.
Yeah.
But I think the general gist of working on semiconductors, getting the structures working within technological frameworks, was a massive leap forward. So we're talking about P and N junctions and things like this, right?
Yeah. Okay, next.
So I've then gone for 1972, superconductivity.
Superconductivity. So I have that one as well. I have that one at number 9.
Good. So we're in the right ballpark again.
Yeah.
So this is what, Cooper?
So BCS, right? Bardeen, Cooper, and Shapiro?
Is it? I'm not sure. So what year
somebody,
is it?
I don't remember. But they did superconductivity.
I feel bad if we don't give like everyone their name. So what have we got? What was the year again? 1972.
Schrieffer is what?
Yes. Nobel Prize, Physics, Nobel Prize for 1972 is Cooper, Bardeen, and Schrieffer.
The second in this case, Nobel Prize for Bardeen.
Oh, that's interesting. I didn't know that.
Yeah.
So what did he get the first one for?
We'll probably get to that.
Okay.
So, all right. So superconductivity. Why is this one? So I think superconductivity, I have it on there as really important because, we use it one thing in medicine. So medicine uses superconductivity all the time for all of the medical imaging. You have to have strong magnets, and in order to have those strong magnets, you have to have a high current. And the only way to get that high current without cooking the person inside the machine is to be able to have it with no resistance. Because as soon as you had copper wires in there, then it would turn into an oven. And we don't want that.
That's part of it. I also had a sort of, along a related theme. I know at the LHC, obviously, to get the magnets as strong as they need to be to do the to just make the LHC operate, you need liquid helium to get down to the superconductivity. So running these huge experiments at very, very high energies requires this to have been discovered and to be technologically viable. So,
and apparently
that's sort of where I was coming from.
There are a few transmission lines that are superconducting. I believe that there's a transmission line that runs roughly down the west coast of the U.S. It's interior to the west coast, but it parallels the west coast of the U.S. that I believe. Okay, wait, maybe that's not it. But there is eventually one of the goals of the energy industry is to have superconducting transmission lines so that they don't lose as much energy in the because right now it's something on the order of 10% of the energy is lost in the transmission, and so 10% of the if that gives you a free 10% of your energy if you can recover it, or 9% or whatever, it depends on what it takes. So yeah, superconductivity, that's up there.
And essentially what in particle physics discovery at the moment, it's going to be essential to have superconducting magnets as we know how to do it at the moment with machines like the Large Hadron Collider or the Future Circular Collider. We're going to need these things to go forward discovering new physics. So that's why I thought it was going to be such an important.
So there was a question from the comment that would they be cooled by liquid helium? And the goal with a lot of this stuff, and this is the reason that it made the headlines 2 years ago or a year and a half ago, the high temperature, like the room temperature superconductivity. So the goal is to be able to find other elements or other compounds or structures that can be superconducting at higher temperatures, so that you don't have to cool it with helium. You can cool it with something else.
So as I understand it, the room temperature superconductor, and I think people at your university did some work on that,
indeed.
Didn't they?
And I know the person. We have lunch quite often.
It's a little bit of a cop-out because...
Oh, no, it's not.
No. It's great work. I'm not
I know what you're going to say.
Any dispersions on the work.
Go
but
ahead.
It's a room temperature superconductor, but it's required to be under the pressure of like having Jupiter sat on top of it or something stupid.
Yeah, it's basically the center of the Earth. Like, it's 300 GPa.
Yeah, so you've taken away one problem, but just brought in another one.
Yeah,
So
no, you kick it down the road. You kick the can down the road.
Yes, it's a great PR job, but
That's
not
a detail for someone else.
It sounds like they've made, you know, a superconductor that you can just chuck into transmission lines or wherever you want, but actually that's not quite the case.
Yeah, exactly. You are right, and they will of course be the first to admit it. So it's a big milestone, but we only have 1 foot across the border. We got to get the other foot across. So yeah, you're right. Okay, next.
So I've gone for 1989 atomic clocks.
Okay, atomic clock. And I have at number 5 atomic clock.
We're not doing too badly then, are we? We're doing okay.
Yeah,
I think the only place we're going to differ is in the sort of definition of what good for society meant, but we're doing pretty well.
Yeah, so we have it in the same spot, atomic clocks.
And the reason I was thinking about things like this was my mind initially went to GPS. So very precise timing for things, very precise positioning. So GPS is obviously huge nowadays. You know, everyone uses it in their Google Maps, and you need extremely precise timing to do various things. And this is something that allowed that to be more common.
Yeah, I agree. It's especially as we become more integrated with the information. Like as our daily lives become more integrated with the information, you know, self-driving cars and drone flying and stuff like that, then and of course when you're searching for axions, like I did, we used the GPS system.
Or when you're looking at faster than light neutrinos.
Yeah, exactly. Those two things. Those two things.
Very, very accurate measurements.
Okay, number 4 for you.
So I thought that was on there. So 19. So if I'm sticking with the tech ones, I'm going to go 1970. Or have I done that one? I've done the semiconductors. What have I got left? I've used that one. So the problem is the other ones I brought in my society, how people feel about being a place in society ones, but I've got the number 1.
Okay, so let me do.
So
let me do the next 3. I'll do the next 3.
If you want to do the little bits, and then I'll bring in
and then we'll see what we do on the next one. So I have as number 4, integrated circuits.
Yes.
So I don't know.
I think I would have probably. This is probably when I went through one that I skipped over because I probably counted that in with semiconductors, but I will accept integrated circuitries.
Okay, so maybe that's your version of the information. My version of your information systems thing is integrated circuits. So I put integrated circuits at number 4.
I think we've hit on the same sort of things that are important,
right.
But there's probably several prizes that lead to the same.
They're kind of part of the same
field
of the same puzzle that eventually. Okay, exactly. I have as number 3 the transistor. That was the first Nobel Prize from Bardeen.
Oh, and then, not really?
Yeah.
He did transistors.
And superconductivity. So I have the transistor as number 3 because that's basically any digital technology is transistors.
Yeah. So I think we've hit on the same themes, haven't we? So semiconductors I think goes in there. Transistors is going to be semiconductors as well. So
okay, so why don't you give me what you have for your remaining 3, and then we'll unveil our number 1 picks. At the end.
The problem is the other ones I've used as the sort of, you know, more wanky nebulous ones.
No, that's fine. That's fine. Go ahead.
Important place in the universe. So I put Penzias and Wilson, 1978.
Okay, so the CMB. Okay.
Because I put that in the sense of knowing where we've come from, how we got here, how everything started. So it was more that sort of nebulous rather than a technological sense. So for those who don't know, Penzias and Wilson, they discovered the cosmic microwave background radiation coming from all directions. So as I understand it, they did it somewhere down in the south of England, and they had a big horn antenna, right?
Was it in England or I thought it was New Jersey?
It might have been in New Jersey.
Because they were from Bell Labs, which is in New Jersey.
I'm so UK centric. Probably
New Jersey. It's like Jersey, right? Maybe it's the south part of
them over to Jersey. Because that's exactly. You know what? Now that I think of it, that's probably exactly what I'm doing, is moving them from New Jersey back to Old Jersey. And they had a big horn collector, and as I understand it, they thought that the CMB was bird droppings in their big horn detector, because it was essentially a fuzz that wherever they turned it around, it seemed to be coming from all directions, and they weren't exactly sure what was going on. So they spent an inordinate amount of time sort of scraping this thing out and getting rid of the bird droppings, getting rid of any dirt. And whatever they did, they couldn't get rid of this fuzz that was coming from all directions. And eventually they realized that actually this was a feature, not a bug, and was the radiation from the Big Bang, which had been stretched out as the universe had expanded, to give this low-level cosmic, long wavelength microwave background coming from all directions. And I just felt, in terms of society, that was a sort of awe-inspiring idea to get back to those origins, and an idea of where we come from. The sort of first solid sort of experimental showing that the Big Bang was real, essentially.
Okay.
So I stuck that in there, but that probably, I would put these down at like 10 and 9 and shove all the other ones up if we're going technology. So I'd probably put that as my 9.
Okay.
And then with that I put in the production of heavy elements in 1983.
Okay.
So I would put the Kellogg, the Penzias and Wilson, and the stars at the 9, 10, 8, 9, and 10, and then I would push all of the ones up that you wanted to talk about with technology.
Okay, so let's see. So
that would get me towards my number 1.
Okay, hold on. So exoplanets moves down.
I'll put exoplanets.
Oh, you cut out.
I would put the Penzias and Wilson, the stars, and the exoplanets at my 9, 10, 8, 9, and 10.
Okay, what stars? The heavy elements?
The heavy elements.
Okay.
Because again, this is, we're all made of stardust sort of stuff, but it's not technological. If you want to talk about technological, put those 3 at the end and shift up all of my technology ones.
Okay, so I'm gonna, instead of calling it heavy elements, I'm gonna call it stars.
Yeah. So essentially I bifurcated my list in terms of what society meant, right?
Yeah.
I put a few that were awe-inspiring, get people interested in science, lay people can understand the implications of these discoveries, and then the top 7 are basically tech-based, so literal applications in society. So
okay,
probably trying to be too clever for my own good, really, with the brief.
No, we'll get there. So I am going to keep the atomic clock where it's currently located, because that way we agreed on the position as well.
All right.
That's the one place where we've agreed on it.
Right.
Actually, if I switch radio and the blue LED for you, so Marconi and the blue LED, then we'll agree on that
3.
one too. So and then
you
got one more.
So right at the top, I've got.
Wait, don't. Is this your number 1?
Yes.
Okay, got to hold on for a second. So let me fill in the gaps of the things we missed. So you've actually got 9, but that's okay. So we'll save number 2 for like the next most important thing that comes in the future.
Okay.
So what I have as number 10 is the CCD.
So the current device. What's the
charge coupled device?
Charge coupled device.
So digital cameras I have as my number 10. We have superconductivity. I've already done. That's my number 9. Number 8 I have as liquid crystals.
What year was that?
Don't know. Something in the 80s probably, because it was Cohen Tanuji I think that did that. So the discovery of liquid crystals, because we use that. That's another kind of display technology type thing that we use all the time. I have the laser.
Yes, I did. So I did think about this one.
Okay, so we'll put your laser as number 2 then.
Okay, then we'll put the laser as number 2, because I did think about that one.
So I have the lasers number 2. I have atomic clocks as number 5. Integrated circuits as number 4, which now matches with your information one.
Yeah.
I have the transistor at number 3. I had radio at number 2. and we both have not yet said what our number one things are. So you're number one.
I think my number one, people might think is a bit lame because obviously it's a big thing at the moment. I've actually gone with 2021, last year's, and I've gone for modeling of climate and global warming because obviously it's a really big issue at the moment. So I've gone with 2021.
Okay.
You wanted a societal issue. That one is purely a societal issue. So I've gone with that.
Okay. And so mine is actually related to that.
Okay.
Except mine is a solution to your problem. And mine is nuclear chain reactions.
We can play nice with those two.
So, so I had as the top one nuclear reactors because I think that's the technology that eventually is going to be the resolution to, the thing that not only addresses a lot of the climate issues, but that also is able to improve people's standard of living around the world. Yeah. So
I don't think we're actually that far off once we sort of get at the themes of what's
like there may be multiple there were certainly multiple things in semiconductors that I had to, and I did probably the same kind of calculus. It's like I can't include all of them, so I have to pick one as a representative.
I picked one as a representation of that block and then like sort of jettisoned all the other ones.
So let's see, which ones do we agree on? How many do we agree on? So we have superconductivity we agree on, blue LED we agreed on, radio we agree on, that's one. The laser we agree on since we added it in, the atomic clock, integrated circuits.
Yeah, I definitely agree on that. I just jettisoned it because semiconductors already done, but I guess there's more. There's more to integrated circuits than just the things that make up silicon chips.
And then I'll say that the number one, we had the same idea.
Yeah. So I'm happy that there's like sort of 6 or 7 there. I think the main trends are there. And this is how I sort of operated in the ones that I thought were most important from a scientific perspective as well. Where there's 6 or 7 that sort of feed into one idea, I picked 1 or 2 that I thought were the sort of culmination of those. Yeah.
Okay, so
but I think that's a pretty good. I'd like to know what other people think as well. Like what they would say was their most important one. In a societal perspective, however you define that, so maybe technologically is what we've led on. But I'd be interested to see what other people say as well.
Okay, so there was one here that's fabrication, plastics, like, and also like nanotechnology type stuff. I can easily see someone saying, the buckyballs and nanotubes and things like that as being important. So, okay. So for the science one, should we go in the same order where you present yours and I present mine, or should I do mine first? I'm gonna do mine first.
Go on. I went first last time, so
I'll give mine first, and then you can tell me why I'm right.
All right.
Okay. So now when I say like these are the biggest scientific discoveries, this doesn't necessarily mean it's going to make a better mousetrap. It's more of this opened up our perception of
understanding of the universe.
Exactly, the understanding of the universe. What I have as number 10 is the proton-proton chain. So, and I think that's the production of heavy elements that you have in your stars.
Basically, yeah.
So how the sun shines, the proton-proton chain is what I have as number 10.
Okay.
Do you?
Yeah, I don't have that on there actually.
Okay.
I went for more sort of big themes, of which maybe there was one in there. So where I started, and maybe we'll start in sort of date order because that's how I've got them here, is I started with Michelson in 1907. And the reason I started with Michelson because it was precise timings of maybe you can bring it up and get the exact wording of the prize, but it was essentially getting over the problem of the ether, and suggesting that there wasn't this sort of cosmic soup that was moving, that things were moving in and out of. It sort of paved the way for special relativity. Yeah. And obviously Einstein had done some work on that.
Optical precision instruments and the spectroscopic and metrological investigations carried out with their aid.
Yes. So what I've given for that is that Michelson was the Michelson of Michelson and Morley,
right,
who essentially allowed light is the same speed in all frames to be something that could happen. Yeah, he didn't see the speed of light change when he did his experiments. I think he looked at, I can't remember exactly what he did, but he looked at light coming from the sun.
Yeah, it was interference fringes as the Earth goes in one direction around the sun versus the other direction around the sun, and seeing how if they changed from one arm to the other.
Yeah, and the speed of light seemed to be constant, which is obviously the underpinnings of special relativity, that the speed of light is the same in all these inertial frames. So I thought what that did at the start of the 1900s was open up that possibility for special relativity. So I put him as the first one there.
Yeah. Okay. And I have the proton-proton chain because that was Gamow, like alpha, beta, and Gamow, I think is the paper. And that's where they basically outlined the theory of how the sun shines. And part of the reason I put it on there is because that was the way of demonstrating, that we don't have to worry if the sun's going to be shining tomorrow or not. And so
you see that, but that's a societal one. I think.
But it's a key understanding to how, how life, the origins, the energy source that provides for the development of life and everything.
So I think what I did is sort of, higher level societal ones you probably put into the science, which is fair enough.
Yeah. Okay. So now what we'll do is I'll go through my list, and if we agree, if what I say is on your list, then you say where it is on your list.
Right. Okay. Fine.
So
where you go now?
The next one I have is nuclear decay. So that is
where is it? I think I have it. So is this is Curie, right?
Yeah.
Yeah. So I've got Curie on there. Yeah.
So, do you have her in any specific location?
I had it roughly around here.
Okay.
So,
we agree perfectly on that one then. So the discovery of nuclear decay, Curie, I kind of included Curie, and then I guess fission would go in there to some extent. I had to choose one or the other, and I went with the nuclear decay. So that would be Curie. The discovery that things can, the heavy elements break apart and release energy as they do, and what particles come off of that is what I have for my number 9.
There was an interesting story I heard about this, was that she got the Nobel Prize, and I didn't know this. It was on Twitter the other day that she got the Nobel Prize. I don't know if this is apocryphal or an urban legend type thing, that she got her Nobel Prize the week before, or very early, or very close to when she had to do her thesis defense.
Right.
I don't know if that is true.
I think it is true. I don't know if she's. So there was another one. It's kind of rough when you get your Nobel Prize for what you did as a graduate student. But I think Adam Rees, who won the Nobel Prize for and we'll get to him because he's on my list. Yeah. But he won the Nobel Prize, and he did it. That was his graduate work.
I'm pretty sure Rees is on my list. I remember which one it was.
We'll get there.
We'll get there.
Yeah. Okay. So I have as number 8. After nuclear decay and the discovery of basically the nucleus and some of the beginnings of how the nucleus works, I have QED.
Yes, so, QED is on my list. So this is I'll give you the year that I've put 1965. Tominaga, Schwinger, and Feynman.
Yep.
For working up QED, essentially putting together the first gauge field theory.
Yeah.
Right?
So QED is quantum electrodynamics. That is the quantum theory of how electrons and charged particles interact with photons. So that was kind of the first complete quantum field theory. Yeah. Up until that point, we had photons, we had Maxwell's equations. It's the equivalent of Maxwell's equations for the quantum realm. It's not going to get more fundamental than QED, and it's been verified.
It took sort of the classical fields and turned them into something to do with quantum. Basically, brought quantum mechanics to classical electrodynamics.
Mm-hmm. So, and it's I think, correct me if I'm wrong, but the way that I at least have internalized it is it was the first complete quantum field theory where, like, this is what it does, here's how the Feynman diagrams work, here's how you do the calculations with them, and then it's been verified experimentally to like 12 or 13 decimal places. And so people are like, okay, let's turn our attention somewhere else now. So it's a field that's probably entirely dead in terms of the development of the theory. There's really nothing. There's no reason to
But
look
just
any
like
further.
this is perfect out of the box. So off we go.
People are still doing quantum measurements and like what are the implications of this theory, but there's no more work on the theory. So I have that one. What I have above, do you have that anywhere specifically, or do you want to have that one at number 8 as well?
So on this one, I kind of went more in sort of date order, but I would say, so where would I have put that in here? I'd have put that about halfway, about number 5.
About number 5, so you'll have QED up here.
Yeah.
All right. What I have as my number 7 is electroweak theory.
Yes, so I've got that basically straight after this one. So I'd put it at about my number 6 or number 4. So right around with QED.
Okay.
Glashow, Weinberg, and Salom in 1979.
Mm-hmm. So I put this one on here because it really was a big change in our understanding of how physics kind of gets put together.
So this was like a first step towards almost a theory of everything, right? Where we were like, we're taking these two disparate quantum field theories and trying to say that they come from a higher level genesis.
Mm-hmm.
So it's sort of the first step towards bringing all of these fundamental forces together under one hat.
Mm-hmm.
So that's why I thought it was really important, because it sort of gave some impetus to that idea of what physics is really, getting right back to the very fundamental ideas.
I put it kind of in the same idea as what happens with Maxwell's equations. So prior to Maxwell's equations, it was like there's electricity, there's magnetism, they're kind of separate things. They appear to be somewhat connected to each other. And then Maxwell comes along and unifies them into one theory that describes everything in everything in electricity and everything in magnetism in one ensemble of equations. And actually, if you do
that's a really nice link. Actually, I think that's a really good way to describe it.
And if you do it if you write it in geometric, what is it called? Geometric physics, geometric mechanics. I just took the book back to the library, but there's another way of formulating physics where it's done using geometric principles. And in that case, Maxwell's equations is a single equation. It's grad F equals rho, something like that. So electroweak theory does the same thing. It takes all of electromagnetism and the weak nuclear force and combines it into one single set of equations that describes both. And so I thought that whenever you take, unifying a set of apparently disparate fields into a single theory was big in my humble opinion.
Yeah, I agree with that.
Okay, so what I have for number 6 is the Cork model.
Yes, got that as well. So it depends how you want to go with that. So I gave
geometric
it to,
algebra. One of the readers did it.
So I gave it to Gell-Mann, 1969.
Yeah, that's what
because there, I believe he predicted was it the epsilon or something, the triple S, that he essentially predicted a new particle, a new particle, which they then discovered by appealing to the idea
the
that
omega
quarks existed. Yeah, the omega. That's right, exactly. I think it was SSS. Or
yeah. So he said that that if things are right, then there's going to be this strange quark, and he said basically, here's this bookkeeping thing, and there's a strange quark, and so if this bookkeeping thing somehow maps onto reality, then there should be a particle that has 3 S's in it.
So he was basically the Mendeleev of the quark model, right? Mendeleev said, I've made this table, it looks like things should fit together in these orders, and here are certain elements that you haven't discovered yet, which you should find.
Right, so Mendeleev was the guy that developed the periodic table.
And then Gell-Mann essentially did the same thing for the quark model. Now he couldn't experimentally demonstrate that these quarks existed. I think that only happened in 1990, the direct sort of deep scattering experiments to prove that quarks actually existed. But he worked up this framework of what we should find, and then we found these things. So we could operate, or we did operate, under the assumption that they existed from there. So I thought that was a really good and using that sort of analogy of the periodic table, starting to make a periodic table on an even lower level for subatomic particles, I thought was a really interesting and important leap forward.
Okay. So I had that as number 6. Did you have
it
anywhere?
Begs the question of whether that will happen again, right? When we get to even higher energies. But for now.
Did you put the Cork model anywhere on your list?
So I would go underneath that. That would be at 4 if you haven't filled 4 out.
So
yet.
It's closer to the top for you?
Well, it's around those. It's around the 6. Maybe put that in at 4, yes.
Yeah, okay. Sounds good. Okay, so above the Cork model, I have the discovery of, so this would be my number 5, the discovery of dark energy.
I haven't got that on mine, actually. But I'm willing to hear you out. So
the discovery of dark energy was, and this is where Adam Rees is one of the recipients of it. Looking at distant Type 1a supernova, they were able to demonstrate that the universe is accelerating in its expansion. So we know that the universe had been expanding because of the cosmic microwave background discovery. And what they did is they had
is this expansion at an accelerated rate?
Yeah.
Because I think I put that into one of my potential societal ones. So
okay.
I recognized it as important, but please carry on.
Yeah. So the discovery of dark energy basically said, not only is there a lot of stuff in the universe that we don't know what it is, but there's even more of it now. And it shows the history of the expansion rate of the universe. So the way that they discovered dark energy and the way that they showed that the universe is accelerating is because if the universe is expanding, so if the universe was static, then a distant object exploding with a particular brightness, that brightness would fade at a certain rate. As a function of distance, it would fade at a certain rate as a function of distance. It goes as 1 over r squared if the universe was static. As the universe expands, then it scales differently. The rate at which things appear to dim with distance changes. And so if the universe gets big and then small and then big and then small, or goes through different changes in the rate that it expands, then you get different brightnesses at different distances. That's a function of basically how do the photons spread out from the original source. And so they were able to trace back, looking at these supernova, map out the expansion history of the universe. And it did a number of things. Number 1 was it showed that the universe was actually older than previously predicted, because when there was no acceleration, you just trace the velocity back to the Big Bang, and that tells you when the starting time is. But when there is acceleration, it means that it was moving slower in the past, and so it extends the amount of time that the age of the universe. So the universe was moving, slower in the past, and so it spent longer at a smaller size, and then started growing more recently. So it resolved tension between the ages of stars in the galaxy and the age of the universe, because we had stars in the galaxy that were older than the previous estimates for the age of the universe. So I thought dark energy was a big deal.
I'm willing to say that out. The one I've got sort of to fill in one of these gaps. So I had like 5 that I had to condense into 1.
Mm-hmm.
So I took 1918, 22, 27, 29, and 32, which are Planck in 1918 for energy quanta.
Okay, hold on. I have that as number 2.
Okay. All right.
So we're getting kind of dangerous here.
All right. Okay, fine. Right. So 1918 energy quanta, 1922 Bohr for essentially the Bohr model
mm-hmm.
of the atom and the radiation that comes from atoms. So electron shells, basically, in mm-hmm. quantum mechanics. Then I got 1927 Compton effect, because light changes frequency, quantum mechanics again. Mm-hmm. And then 1929 Dubois for Dubois wavelengths showing wave particle duality. And then I've condensed all of those down into 1932 Heisenberg for the formalism of quantum mechanics, basically.
Okay. So the development
all of those I think are important,
uh-huh.
but I've chosen as the representative for those what they were all leading towards, which uh-huh. was the 1932 essentially Copenhagen interpretation of quantum mechanics.
Okay, and so I went the opposite direction. I had the same thing, and I chose Planck as the representative.
As the sort of representative. Right, fine.
Okay, so where do you put the development of quantum mechanics? I have that as number 2 on mine.
So it would be going down again. So 3, I guess.
3. Okay.
So yeah, pretty close.
Okay, so let me do my number 4 and my number 3. and then we'll reveal number ones, our number ones, if they're different. Okay, so I have as number 4 the cosmic microwave background.
So you brought it over from the societal one,
right?
So, okay.
So, and that was the evidence of the Big Bang. So we have the Big Bang, and then dark energy is kind of related to that. I thought the CMB was a bit more important than the discovery of dark energy, because the CMB really changed our perception of how the universe was, how it started and how it evolved. So,
see, I can feel in this your sort of your astrophysics leaning sort of start to come in, whereas I put them in the societal ones because I can see how awe-inspiring astrophysics discoveries and astrophysics is.
Yeah.
So that's why I decided to put it over there. Whereas when you're in the field, you see it as
revolutionizing the field.
thing, I guess. Yeah.
And,
exactly.
and there's, I'm sure, I only have 2 spaces left right on my list, and there's a whole bunch of material science and type things like Laughlin liquids, and that I don't boson. I probably shouldn't give this away. I don't have bosons.
We should say and be very clear about this, that and I said it at the start, there's no right and wrong answers, and there's a hell of a lot of important things in there where I probably haven't done enough research on it or know exactly how influential it was. And that's why after this video, during this stream as well, I want to hear from the viewers and see what they say as well, because there's a hell of a lot of good science in there that we won't have even touched on.
And our interests have a fair amount of overlap too, so
correct.
Okay, so we're
hopelessly biased on the importance of the list.
I have at number 3 the positron.
Yes, I've got it in there. So I think that would have been earlier on my, probably, I don't know if you've got any high spots left.
I've got a 7 and an 8 left for you.
Right, go for an 8 for the positron.
Okay, positron.
So yes, so discovery of the positron, Anderson, 1936. And Dirac. Essentially this, Did Dirac win it with him? Because he was the one who
proposed that it should exist.
Proposed it, but then I don't know if he got recognition for the proposal or Anderson just got it for the discovery. It's a beautifully, really, really simple, actually, method of discovery. So obviously an electron or a positron is going to curve when it goes through a magnetic field. So he set up a magnetic field to try and catch the curvature of electrons or positrons. Now, a positron would obviously curve in the other direction. The problem for this experiment was, if you see something that curves in the opposite way to an electron, was it just an electron that came from below as opposed to an electron that came from above? How would you know the difference between an electron that came from above or a positron that came from below? And what he did was he broke the symmetry of the situation by putting a little sheet of metal in the middle of his magnetic field. And what you could see is, when does the curvature become more steep? Because it's lost some energy from smashing into the metal bar. So you can break that symmetry. And he saw
it curves. So before it impacts the metal, it's got some curvature, and then it hits the metal and slows down, and then it's got a different curvature.
And it has a much stronger curvature.
Oh, that's cool.
Yeah, exactly. So then you can see whether it came from above or below, depending on where the stronger curvature is. And then you can break that symmetry and see if it's something that's curving to the right or to the left, clockwise, anti-clockwise, in the magnetic field that you know, and therefore whether it's positively or negatively charged. It was a very beautifully simple experiment to find something incredibly profound. And the reason I put it on the list was because it opened up, again, another huge array of particles. The idea of matter and antimatter therefore comes in later, the idea of CP violation, the origins of the universe and why matter and a hell of a lot of light are here. So I thought that was an incredibly important discovery. And it has the underpinnings as well towards the quantum field theories as well, because you have the Dirac spinners basically predicting the electrons and positrons. So I thought it was an incredibly important discovery. Maybe I think Dirac should go in there with Anderson for that. So
okay, so my number 1, and this is probably where we're gonna.
No, not number 1. We got some spaces to fill out.
But I've already done all the rest of mine. So
okay, right. Okay, I'll fill out a couple of ones that I had left.
Wait, hold on, because we might agree on it. So I'm gonna need to give my number 1.
You do your number 1 then.
Okay, And
then we'll discuss some honorable mentions.
And, yeah,
we'll agree
and
on the one, and then we'll do some honorable mentions.
And then you can tell me why I'm wrong, or you can tell me why you're wrong on this one. So I have as number one.
So hold up. How old is it roughly?
Not very old.
Okay, so we disagree.
Okay.
But all right, go ahead.
So should we do since we disagree? Then do you want your number one to go first, and then mine?
I don't mind. Whatever you want. You're the host.
Okay,
so
I'll say mine and let you have the last word on what you think number one is.
No, you get the last word. You're the host.
Okay. So what's your number one?
I've gone, and people might find it quite boring, but I've gone for 1921 and Einstein.
Einstein.
And the reason I've gone for this is because it felt like a Lifetime Achievement Award for his 1905 work.
Like Peoples.
Yeah, basically like Peoples. Yeah. So he hadn't had the Nobel Prize for his work in 1905, which a lot of people don't realize. But that 1905 work had Brownian motion. It had the photoelectric effect, which is essentially the underpinnings again of quantum mechanics, showing quanta of light. It had special relativity as well. Mm-hmm. He had so many huge...
Yeah, the miraculous year.
Yeah, the miraculous year, as it's called. Had so many massive inputs into so many important discoveries that happened over the next sort of, 30, 40, 50 years. Mm-hmm. Quantum mechanics, special relativity. And then he had Brownian motion that nobody seemed to really care about, which was kind of a cool little paper.
So the Brownian motion, let me jump in real quick. I think that the Brownian motion it's underrated. It's underrated today because I believe that Brownian motion gives you the size of the atom. I think it demonstrates the atomic nature of matter. So before then, people were like, there might be atoms, and we're not talking about like the structure of the atom. We're talking about the existence of atoms that they had been proposed, but there was no way to see what they were.
So we should probably tell people what this is, because it seems incredibly simple, but it was the idea that I seem to remember it was with pollen grains.
Yeah, I think it was pollen.
Why do pollen grains dance around
in the air,
on the surface of water? Like, why do they random walk all over the place? Why do they not just sit there or move with a wave that happens in the water? Why are they constantly random walking around the surface? And the idea was that something is hitting them. These balls, these atoms must be hitting them. And he suggested this and then beautifully demonstrated how the maths would work out to make these pollen grains dance around on the water if there were these as yet undiscovered tiny balls that were impacting them. Mm-hmm. So you're right, much deeper meaning than just pollen moving around in water.
So people had always had this idea, like it goes, because atmos goes back to the Greeks. They had an idea that there could be an indivisible thing, an indivisible substance, or you take a substance and you can divide it down to some indivisible element, and that was called the atom. Yeah. And but it had never been demonstrated that what they were, like that they actually existed. It had been hypothesized. It was kind of a working model that people had been using. And Brownian motion, so this random motion that you get from the collisions of your target object with the surrounding environment. Einstein predicted if there are atoms, he basically said if there are atoms and those atoms are bumping into it, then you'll get this motion, and it matched what was seen, this random motion. So that was basically the discovery of the atom. So yeah, I don't have Einstein on here. Part of the reason I don't have Einstein on my list is because he made so many contributions that.
This was the thing. When I said it, I imagine a lot of people just went, "Oh, Einstein wins," but the reason I put it on there was
he wins
exactly
for a reason, right?
Reverse. Yeah, he wins because there were so many contributions that I couldn't unpick them and give them all to somebody else. I just feel that he did so much, and people hate this idea of the lone genius and blah blah blah. But there were so many huge, and you've just expanded the Brownian motion into something that was actually a lot more profound than even I'd kind of realized. He had so much impact on that period, and the underpinnings of so many things coming forward from that in terms of quantum mechanics and special relativity and general relativity. Yeah. Let's not forget that I couldn't not put it as the number one. I couldn't think past it.
So who else among all the Nobel Prize winners, who would be the other kind of lifetime achievement awards? So I think Peoples kind of got a lifetime achievement awards, and I think Chandrasekhar also got kind of a lifetime achievement award for like all the things that he did.
Was there?
They didn't really do that, right? So Einstein got it for the photoelectric effect, which was kind of
which was an odd choice out of all of the
for him.
It's like special relativity,
but they had to do something
general relativity.
Early on it was tied to experimental results, and so
true, because they couldn't necessarily test a lot of these things, so that might have been why. But there've been changes, as you say, about the reasons for giving these. So yes.
Okay.
But I couldn't get past that. I don't know what you put.
No, so my number one, it's related. It actually is related. My number one for like the most important scientific discoveries in terms of just like the profundity of the discovery, gravity waves.
I think you brought your societal ones across to mine, but I think those would have had an honourable mention in my societal ones, because again, it's one of these ones looking out into the universe. Do you want to? You know so much more about this than me, so do you want to?
So the discovery of gravity waves. This was recent, and Einstein had predicted that in general relativity that you would get radiation that comes from the in spiral of different things, but detecting gravity waves is really hard because you're basically looking at you're looking at the overall fluctuations in the path that photons take from a distant source relative to a distant source. And I
seem to remember, if I think back to my astrophysics lectures in the final year, some freezing bar that was suspended.
Yeah, a Weber bar. So like a bar of aluminum, and they were looking for it, and then there are a bunch of different gravity wave type detectors, and none of them were remotely sensitive compared to LIGO, but they. If there's a source of gravity waves, it
was a two-way spectrometer, right?
It was a Michelson interferometer, right? So that's coming full circle.
So he deserves to be on there, you see.
So and they detected these gravitational waves, and I should point out, it's gravitational radiation is the technical term, because gravity waves had already been co-opted.
So you see it as a shift in the interference pattern of
right,
the two beams,
a tiny one. Right? So the gravity wave, LIGO gravity wave detector, it's detecting variations on the order of 10 to the minus 18 meters. So that's one. How
do they rule out a truck going by and all these kind of things?
Exactly.
I need to have a look at I need to look more at the experimental setup. I always found it amazing that you could get down to that.
Yeah, so they do it with a lot of photons. Basically, you average over a lot of photons, and then you have ways of mitigating all the other rumblings that are going on. So they can detect the moon going overhead. They can detect the waves crashing into the beach 200 miles away. They can detect antelope jumping over the things. They can detect the redneck that smashes his truck into the side of the building. That's
probably huge compared to the antelope. That's probably a huge thing in there.
Yeah. So what they can detect with this is amazing, and they can detect. So we're actually watching black holes spiral into each other and giving off this radiation. We're watching like the entire sun's mass worth of energy, E equals mc squared. You take the sun's mass, which is 300,000 times the Earth mass, and it vaporizes, basically vaporizes into gravitons, into energy over the course of like a quarter of a second. And so in less than 1 second, you have a whole solar mass worth of energy just getting burst out and sent out into the universe, and we're picking it up here 150 megaparsecs away. It's a completely different way of looking at the universe. It's a different source where there's no other way really to measure them. We can measure like the Holtz-Taylor pulsar kind of stuff. We can measure the general relativistic decay of certain things. However, those are just like trophies as opposed to a whole other way of observing multiple sources across the universe. And it's really profound. It's kind of the final demonstration of how good Einstein's theories were, the technology that went into producing it, and just the overall simplicity of the signals that they're looking for. And I say simplicity in the sense that it's two massive objects that are spiraling into each other, and as a consequence, warping space-time. In terms of like how do you calculate the in-spiral of these things, it's a highly nonlinear theory, and so the calculations are challenging, but the setup is just you have two supermassive, super dense particles. They spiral around each other. They give off radiation that distorts space-time, and we see that. I think it's just a huge breakthrough.
So I'm going with and people who are watching might think we're sort of massaging this a bit, but I'm going with the idea that you've put Einstein at number one as well, because essentially what you've done is a demonstration.
It's the bookends of the whole thing.
It's the bookends. We put one of each bookend.
Yeah, like climate nuclear reactor, right? Those are the.
Yeah, exactly. I think we've been very, very similar on the sort of the topics that we think are the most important. Now, I wanted to mention
you have two more. You have two more.
I've got two more. Okay, good. So I get to add in some more. So I went with 1945, Paulie exclusion principle.
Okay.
And the reason I went for this because it showed that
I put him at number 7.
You've got him at number 7.
No, I put him on there for you at number 7.
Okay, good. And the reason I put this was because it showed that there's a fundamental limit, not just an experimental limit, but a fundamental physics limit of how accurately we can know certain quantities. So it changed the actual way that we had to think about quantum mechanics as a kind of statistical and limited accuracy theory. So I thought that was a very important thing. Obviously, it has a lot of implications for spectral broadening and things like this. So I thought that was a very important discovery. And then another one that I put in there, I don't know. I'm going to let you choose between these two. So I've gone, and I think I know which one you'll go with. I've gone 2015 Neutrino Oscillations, or, and I'll allow you to choose, 1980 CP violation by Fitch and Cronin.
Oh man, those
might
be related to each other. It might actually be that those.
That's what I mean. Right, exactly, and that's why. So CP violation, for those who don't know, and I'm biased because this was my field of research, is the differences between matter and antimatter, essentially, and trying to understand why all of the protons in our universe are positive and not negative. Why did the universe decide to discriminate one way over another? Why is matter and antimatter very slightly different? And Fitch and Cronin demonstrated this with K mesons in 1980, and it was essentially the first experimental. If you could ring up somebody in an alternate universe, it was the first thing you could say to distinguish plus from minus. You would say, we live in a universe where the K meson does this in this way, and define plus versus defining minus. So it was the first demonstration of how can you label plus versus minus. And I thought that was a very big discovery because CP violation obviously impinges on universal origins. It showed that there's a discrepancy between these two sets of particles, which is again another place where we have to do a lot of investigation. And I thought that was very important on the list. And then obviously going forward to neutrino.
Yeah, so let me make the case for neutrinos. I'm going to make the case for neutrinos before I make the judgment.
Okay.
And so with neutrinos, we have this particle that was predicted a long time ago, and
I can give you a free out, by the way, because Anderson has got some of the sort of antimatter-y stuff in there, so maybe that's a way we can sort of work them both in.
So and the idea was that every generation of leptons, so the electron, muon, and tau, has its own neutrino, and those would be produced. And it was important early on to understand, like, neutrinos became a big deal for understanding the sun. So what we have in here, what you have as your number 10 from the previous subject, and what I have as number 10 for this one, is how the sun shines, the generation of heavy elements in the sun, and the proton-proton chain. And in order to verify that this is indeed how the sun shines, you have to look at the neutrinos coming from the sun. And this was done in the 1960s, and they didn't see what they expected to find. They expected to find 100%, and they saw like 30%. And throughout the course of the 80s, they were still trying to figure out like where are all these neutrinos going. What the solar neutrino problem was a 40 some odd year discrepancy between the predictions from the solar model, which matched a whole bunch of other observations like helioseismology and stuff like that. And then the observations from the neutrinos that are coming directly from the core. So that's the reason that you want to study neutrinos, is because they come directly from the core of the sun. They don't come from the surface of the sun. All the photons come from the surface of the sun, and they're already 100,000 or like 1 million years old by the time they get there. So they're
that's
a million
a really
years old.
Cool thing. You can't just skirt over that, because people often don't realize this, that the mean free path of a photon in the sun is like tiny, right?
Yeah.
The photons that get generated in the center of the sun take like millions of years or something stupid. I can't remember what the exact number is.
So I say 1 million years, but I think it's closer to like 300,000 years.
Yeah. So they take an inordinate amount of time, and because the photons are essentially bashing into electrons and what have you in the core of the sun, and they have this tiny mean free path to get out of the sun. And I don't think a lot of people realize that. They don't just get generated and then fly out. It doesn't work like that.
Yeah, and so where the neutrinos, those do get generated then fly out. So while the photons are 1 million years and 8 minutes old, the neutrinos are only 8 minutes old. And so it's actually watching in real time what's happening in the core of the sun. Another thing that's useful, like a useful heuristic to keep in mind, when you talk about the early universe and how the early universe was this really hot plasma with photons and everything, dogs and cats living together, all sorts of mass hysteria going on.
That's Ghostbusters.
Yeah, the typical photon. So when we look at the cosmic microwave background radiation, we're looking at photons that originated from the electrons combining with the nuclei in the early universe and releasing some energy at that point. Like the energy that went into forming the atoms is released, and we're seeing that today. The distance that the photons traveled from the Big Bang to recombination, which took place at like 400,000 years, that's roughly the solar distance, the solar radius. So the early universe happens, you have this opaque plasma, like a lightning bolt. You have photons bouncing around inside of it. And after 400,000 years, recombination happens, and now the universe is transparent and the photons can escape. And that's basically what's going on in the sun. It takes 400,000 years for photons to go from the center of the sun to the surface of the sun. And so the particles were really bound because 1 second after, it's not quite a second, but a couple seconds after, it's 400,000 years, the photons are all bound they're bouncing around in some small neighborhood. When recombination happens, 2 seconds later, they've traveled a greater distance from their point of origin than they had in the previous 400,000 years. So the neutrino oscillations allowed us to peer into the sun to see we can study details of the chemical composition of the sun's interior based on the neutrino spectrum. But it needed to be resolved first because we weren't seeing the neutrinos we were expecting. And so we needed to figure out what is actually going on here. Why don't we see the neutrinos? And it turned out that they were switching from one type of neutrino to another, which was not predicted from the standard solar model. Or from the standard model of particle physics. So the neutrinos were switching from one type of neutrino to another, and then our detectors weren't designed.
Because they have to have mass to be able to do so.
Yeah.
And it was always thought that they were massless.
Mm-hmm.
But in fact, it turns out they do have a mass hierarchy, and therefore they can switch back from one part to another. So by the time they were reaching us, we're trying to detect all of these electron neutrinos, and some of them aren't electron neutrinos, so they're not interacting with our experiment in the way we expect, and they are missing.
Yeah, and so it's kind of like the way that neutrino oscillations works is similar to how polarized light works. So you have a polarized light source, and you can't, if you have a detector that is perpendicular to your polarized light source, if you have a polarizer that's perpendicular to your original source, then you don't see anything on the other side. Yeah. And the only way that you can get the light that's polarized in one direction to be visible in a different direction is if you put the polarizer in, you have some other angle, some other basis that you can transform to and then transform back from. And so the neutrino oscillations, the mass of the neutrino gives you the second basis where you can start with the flavor basis and then it propagates in something that has some rotation to it, some other basis. And then when you transform back at the location of the detector, you're rotating back to the original basis, and in the process of doing that, you've lost some fraction of the particles that were originally emitted. That's the first time I tried to explain that. So I'll need to think my way through this.
They interact as a kind of superposition of all three types of the.
So I'll need to think about that one and work my way through that explanation again before I teach it to my undergraduate students. But anyway, so neutrino oscillations, it was a huge deal, and it was found first with the atmospheric neutrinos and then with the solar neutrinos. Okay, so the winner.
So the reason I put that in, by the way, is because it's beyond standard model physics, which shows the standard model is not complete, as many other things do, to be fair. But it also shows that there's hell of a lot of work still to be done. Mm-hmm. So I thought that was a very important thing to put in there. Okay,
so what I have for your number 2, if picking between these two things, is CP violation.
Okay, we'll go CP violation.
So I think CP violation is a bigger deal than neutrino oscillations, partly because neutrino oscillations could have been just part of the standard model from the beginning if they just give the neutrinos mass. I'm sure it's not quite that straightforward, but this is our stream, so we can declare what they should have done.
It's been a while since I did the neutrino stuff, so I'll stay quiet on that.
But the CP violation, I think, is certainly a more fundamental issue, because it really gets down to why are we made of matter,
and not antimatter.
Yeah, and not antimatter, or why is there anything at all? Comes down to I believe CP violation. I think most people agree that CP violation is the mechanism that led to the matter-antimatter asymmetry in the early universe that allowed matter to persist and therefore us to exist. And so I think CP violation is a big deal, and we don't understand all of the sources of CP violation. We have a number of sources of CP violation, but
they
we don't know,
add up to enough to
explain what we observe. So now, as part of that, one of the experiments right now that's going on in the neutrino world is designed to detect the delta, the CP violating phase of neutrino oscillations between nu2 and nu3 or something like that. Okay. So there's a number of experiments going on right now in the neutrino sector looking for measuring how strong is CP violation in the neutrino sector. I know
this is where you think it is. This is your
This is where my money is, because I don't have any other ideas, and I don't know enough. I don't know enough about the field to be able to propose anything else, and so I'm like, it's probably neutrinos.
Yeah, it's in the place we haven't done enough looking yet. Yeah.
So I think
it's always the last place you look.
Yeah, and so as a consequence, it's conceivable that CP violation and neutrino oscillations are actually the same thing, or part of the same thing, because it all goes into the same matrix. The neutrino mixing matrix, the CP violating phase is part of the neutrino mixing matrix. So that is.
So I think our lists were pretty.
We have. What we have is the same. So you have Michelson in there. I didn't include Michelson in there directly, although
But I think
I'm
did,
sympathetic
because
to
you
it.
had Einstein, you had Michelson with the
gravity
interferometer,
waves.
So with gravity waves.
We both had nuclear decay. We both have the positron. We both have quantum electrodynamics. We both have electroweak theory. We both have the Cork model.
Weinberg, by the way, I think he passed. Did he pass away this year? Last year? So, it must have been last year now. Incredibly fascinating guy.
Mm-hmm.
And people speak incredibly well of how intelligent he was and how nice a chap he was.
Mm-hmm.
Made me want to kind of find out a little bit more about him. I don't know too much about him as a sort of person and his wider work.
Mm-hmm. We both had, I had the cosmic microwave background on this list. You had it on the previous list. The positron, we both had. Quantum mechanics, I had Planck. You had Heisenberg on the other side.
Heisenberg, but basically Planck was rolled into it.
So quantum mechanics I had that as second. You have CP violation as second. And honestly, I can see CP violation is more fundamental than quantum mechanics. Right, it's really getting down into the real nature of
you can't do
how
any
things are put
physics
together.
If you're not here, right?
Right. Well, it kind of. I mean, it's more fundamental, right? It's like space time. In one case, it's kind of a description of how we'd say something. In the other case, it's it doesn't matter if we have a description for it. It's something that exists whether we have a theory to describe it or not. So CP violation, that I don't even have that on mine, so that shows how little I know. But yeah, I put that up there. And then I have gravitational radiation. You have Einstein at number 1. So that's pretty good.
List,
now, one of the things that came up in our discussion that you mentioned was deep scattering. And this was news to me. What is this deep scattering thing? Well, and I'll throw this out to anyone in the chat or who watches the video.
So 1990 prize, I think
one second. So anyone else have anything that you'd like for us to cover, like the things that we missed, which is probably nothing, except for all the material science stuff? Go ahead and say so.
All the condensed matter physics has just been right.
Yeah, Laughlin liquids and Bose-Einstein condensation.
I'm not really sure what that is. That over there.
Okay, so deep scattering. What qu'est-ce que c'est, deep scattering?
So on deep scattering, as I read it, and I quickly went over it because I'd already given the entry on the list to Gelman. It looked like it was 1990. If you want to bring up the prize, just to check. So 1990 looked like it was the demonstration, the scattering experiments that basically showed that quarks exist. So you get the
okay, so this is Friedman, Kendall, and Taylor.
Yes, I think so.
Pioneering investigation concerning deep inelastic scattering of electrons on protons and bound neutrons, which have been of essential importance for the development of the Cork model in particle physics. So what does a deep scattering look like, and how does it tell you that the quarks exist?
So you get this. So just like you get a Rutherford scattering from a sphere, right? This you get the same. If you go up to higher and higher and higher energies, you start to see this similar Rutherford pattern. As I remember it from when I did it ages ago, you start to see a similar pattern that there's balls that are even tinier inside the proton. So it was essentially a demonstration and an experimental demonstration that the scattering is like from hard balls when you get down to very very
so it's
short distances.
It's the substructure of the nucleons, essentially.
Yes.
Wow.
That's how I read that prize, and that's how I remember it. So I thought that was, but I'd already given it to Gelman in the same vein, right? It was essentially, it sounded to me from how I read it that it was the experimental validation of Gelman's quark model. So and you're making me say quark, which I hate, quark model. So I gave it to Gelman as the representative out of those two.
Okay, so that's cool. I didn't. So that's part of the reason I skipped over it. As I was going down, I was like, deep inelastic scattering, who cares? But so that makes sense. I will say that I wasn't paying much attention in 1990. I was transitioning from junior high school to high school, and at that point, the biggest thing that had happened in my life was globally was watching the Berlin Wall fall that November before. So, but there we go. There's our list, and we actually have a lot of similar things in there. Honestly, here's something that's a little weird. That you might find a little weird. I don't include my own discipline on either of these lists. So I don't put exoplanets on either of these lists.
Oh, okay. So specifically exoplanets. Okay, right. I mean, I think you've got the same impetus that I've got of these very important, far-reaching ideas that people find very awe-inspiring. You had a couple like that. I think gravitational waves potentially goes into that box. I think CMB kind of goes into that box. Dark energy goes into that box. These are topics that people who are not experts in the field find extremely interesting.
So the awe-inspiring things, right?
About. The awe-inspiring ones. The ones that sort of Dave puts on his videos and people really like to know the sort of fundamentals
of. That's Dave Kipping, by the way.
Yeah, even if they don't know the deep physics of it. I think these are things that people say, wow, physics is really awe-inspiring, very, very interesting. I want to know more. Whereas if you talk about, Bragg diffraction from a crystal, they just sort of fall asleep. So I think these things have their societal uses, which is why I put them on the list on the society side.
All right, very cool. So, with that in mind, we should you had another list of topics to go over that I think we should put it on hold and come back and revisit it at some point.
we can do.
We'll do a rapid fire of things
should do a quick rapid fire
of stuff that came in the news.
So I saw 3 astro topics, and obviously you're one of my astro go-to guys. So I saw Elon has a rocket that's going to smash into the moon, doesn't he? I don't know if you can Google that and see if that's still a thing that's going to happen.
Okay.
So everyone seems to be losing control of their rockets. The Chinese are smashing them back onto the Earth. They might land on your head. And I think Elon's SpaceX has got one that's out of control that is due to smash into the moon. The last I saw.
Okay, it says Elon Musk's space rocket on collision course with the moon.
Yes.
It will be minor, and if it is possible, similar impacts have taken place unnoticed. It's a rocket that blasted off 7 years ago and was abandoned in space after completing its mission. Will crash into the moon in March, experts say. And we know how much we trust experts these days. The rocket was deployed in 2015 and put into orbit a NASA satellite called Deep Space Climate Observer. Since then, the second stage... I'm reading from Al Jazeera, because that's the first thing that came up. Since then, the second stage of the rocket, or booster, has been floating in what mathematicians call a chaotic orbit. Chaotic orbits exist in any three-body problem, in all but very few three-body problems, three-body interaction problems. And it was Gray who calculated the space junk's new collision course. And that's chaos is something that has to happen before an orbit goes unstable. So they figured out it's going to crash into the moon. And given that background, that it's in some chaotic orbit that will eventually take it to the moon, it probably has happened before, and probably several times.
Yeah.
Okay. So
I need to do a calculation of how big or how fast this thing has to move to beat the GMM over R, the amount of energy that binds the moon to the Earth, right? And
it would probably punch a hole straight through the moon at that rate.
I was going to say you would have to probably beat the structural integrity before then, and
so it's like
or the velocity would go above the speed of light. So I'd have to make it relativistic.
So it's like from that scene in Teenage Mutant Ninja Turtles when the guy's like, "I'm not sure if structurally speaking, this is such a good time for your buddies to drop by."
Yeah.
Okay,
so I thought that was interesting. Probably in the end is pretty much nothing, but a lot of people got upset about that. The other one I saw was yesterday, actually. An isolated black hole just drifting through the universe has been discovered. Any thoughts on that?
So
you were talking about
I do have some thoughts. It's actually, I think it's going to be the topic of a near future stream, maybe even the next stream, because I'm kind of running low on material. So this isolated black hole is like somewhere around 7 solar masses, was detected presumably from its lensing. I think it was the lensing signature. Yeah. So they look at the galactic center, all the stars in the galactic center, and one of them was getting brighter and brighter and brighter over time, and then it was getting dimmer and dimmer and dimmer over time. And that is because of the gravitational lensing of an intervening object. And that intervening object is this, I'm going to go with 7 solar masses because I think that's what I read. 7 solar mass black hole that's passing along the line of sight in between us and the distant star.
How are they measuring that mass if it's not got anything orbiting around it? And to get a radial velocity measurements and things.
I think it's pretty well determined. The lensing equation has the mass as part of it. So it's got the mass and the distances, and then they may have come up with a way of getting the distances, and then the mass is the only thing that's left over, something like that. So I trust their ability to do that because that's what you do with a number of other microlensing type events. And to me, what was most interesting about this is that it's 7 solar masses. And 7 solar masses is in this window. So if you go back to the 1990s, there were two main branches of dark matter candidates. One of them was WIMPs, weakly interacting massive particles, small subatomic particles that have some mass that contribute to this thing. The other one was called MACHOs, which is massive compact halo objects.
Yeah, I remember that.
So massive compact halo objects, these are unknown things, not made out of regular matter, because if they were made out of regular matter, it would have affected the early universe chemistry, the early universe nuclear physics. So the Big Bang nucleosynthesis would have been different if had it been made out of baryons. So it's not made out of baryons. It's not made out of protons and neutrons and stuff like that. And so black holes is a candidate, or any other compact object that's not made out of regular matter, or that we wouldn't be able to tell if it's made out of regular matter or not. So machos, so they did a bunch of surveys in the late 1990s and early 2000s looking for microlensing events, which are these kinds of lensing events from black holes passing along the line of sight and lensing a distant object. There are other places, so there's two ways to look for machos. One of them is that weak lensing, or the lensing signature. The other one is you look at the ionization of binary stars in the halo. So when I say the ionization, I mean you have binary stars, so these two stars that are going around each other, and if there's a black hole that comes by, or like a massive compact halo object that comes by, then you can break up those binaries. And so you look at the distribution of...
so ionization, like being kicked out.
Right,
like
so you kick out, you strip off these two stars that are orbiting each other, you ionize it, you break the bond between them, and so now they're two free-floating stars instead of two bound stars. So that's what I mean by ionization. And so you have this, you look at the distribution of orbital periods of wide binaries in the halo, and if there's 100 solar mass black hole, we'll call it a black hole, but it doesn't have to be a black hole, but we'll call it a black hole. If you have a 100 solar mass black hole that goes by, then it will ionize, it will strip those things from each other. And so you would look for a cutoff in the orbital periods of wide binaries in the halo. And so the microlensing things were creeping in from the left. From the small scale microlensing events that would be very plentiful, those were excluded down to like 10% of what you need in order to explain the galaxy rotation curve. So they can, if they do contribute, so small black holes, if they do contribute, and when I say small black holes, I mean or small machos.
So if they contribute to dark matter.
If they contribute to dark matter, then they can only be up to something like 10%, 5 or 10% of the dark matter, and the rest of it has to be something else. And if you look at really massive ones that would break up these wide binaries, then those also can only contribute up to about 10% if their mass is larger than about 100 solar masses. But there's a window between basically 1 solar mass and 100 solar mass. And in particular, the peak of that window, where the constraints are the weakest, is at 10 solar masses, or right around 10 solar masses. And so they discovered this black hole, and it's conceivable that it's not actually a black hole. It's conceivable that it's something else, this massive compact halo object. But black holes are kind of what people have in mind. So we'll call it a black hole because that's the only object that we have that could match this description right now. So you have a black hole that's 7 solar masses. It's right in that window. And so if these things actually turn out to be common, then they could be the dark matter. At least in the galaxy, and that would change a lot in terms of first of all what particle physicists have been doing for the last 20 years. It would change a lot there.
Making up new particles with new fields
so it's the gravitino
have a stable particle at the bottom, which is always the dark matter candidate.
So the first thing that I thought of when they saw the black hole, and I was like, okay, fine, so they saw this black hole, but when I saw 7 solar masses, I was like, holy cow, that is a big deal.
Okay, maybe we need to talk about this a bit more, and I'll do a video then. If it's got much deeper reaching implications, we can. Talk a bit more.
I think I'll do put together a stream of my own. I spent a couple minutes looking through the literature trying to find the most recent results on constraints on machos, but this is where, at least 5 years ago, when I last looked at it in some detail, this was where that window was.
Cool.
Okay.
And then the other one I saw, if you've got, how's your time?
I'm good for a few minutes. Yeah.
All right. Was the I don't exactly know what it was. I just saw the article. It was actually one of the researchers was one of my supervisors at Cambridge, Natasha Hurley Walker. It was a low frequency. Was it a radar source or? Let me see if I can find the link. It was another paper, and it made it into the BBC this week. So let me see if I can find it. BBC. Find spooky spinning object in Milky Way. So let me send this to you, and you can bring it up. I'm putting it in the chat on Skype. This one.
Milky Way. All right, Australia scientists find spooky spinning object in the Milky Way. News I can trust. The object, first discovered by a university student, has been observed to release huge bursts of radio energy for a full minute every 18 minutes. Objects that pulse energy in the universe often documented. Objects that pulse energy in the universe are often documented. Okay, but researchers say something that turns on for a minute is highly unusual. Aliens. The team is working to understand more. First discovered by an honor student in a region of Western Australia's Australian outback known as the Murchison Wide Field of Array. So the MWA, is like this radio antenna network. The antennas themselves are kind of suitcase-sized, little spider-looking things. They've got it's a three-dimensional set of
like
X's.
Aperture synthesis kind of thing.
Yeah, so then they're all detecting things, and they're a phased array, so they look at the radio signal coming from a bunch of different directions. I have a couple friends who worked on them. You see pictures of the things, and you're like, "Wow, that looks amazing," and then you find out that it's like a little metal contraption.
It's just like a horn, like a little metal horn on a stick.
Yeah, so there's this YouTube group that drops things from heights in Australia. Is it Dude Perfect?
I've seen things like.
Okay,
this.
so there's this group of, I think they're Australian, and they drop things from this tower, like drop a bowling ball into a bunch of
see how it smashes things up.
Oobleck and drop a car and stuff like that. Well, I was watching one of their videos, and I saw a bunch of these MWA antennas in the background on one of the videos. Of course, they didn't respond to my question, but I have one of those. I have a few hundred followers, and they've got like 80 million followers or something. Anyway, so the spinning object every few hours turns on and off the universe. So once every 20 minutes for a minute long, it turns on and off. So it's a slowly spinning object, as opposed to a pulsar. If it was a pulsar, it would be going around. Those spin every tenth of a second or so, or like a few seconds. And this is every 18 minutes. This thing comes around. About 4,000 light years from Earth, which is pretty close by our standards. Extremely strong magnetic field, which they can probably measure by looking at the atomic lines that come from.
So some sort of Zeeman effect or something on the spectral lines, or.
So more detections tell astronomers whether this is a rare one-off event or something that we should look for. Now, this is something. A lot of these kinds of detections, like this once every 18 minutes type detection. One of the reasons we're finding them is because we now have the capability of doing time domain astronomy, where we're looking at something varying over, we're monitoring something continuously for a period of time, or like a huge chunk of the sky continuously for a period of time. And so this is a technology that really wasn't around in the 50s, not to the same degree that we can do it today. And so the same thing is true like with that extraterrestrial asteroid that came through. That was something that we wouldn't have been able to detect 20 years ago. The probability of us detecting something like that 20 years ago was pretty small. And so the fact that we build an array of telescopes like pan-stars, and we monitor the sky every night now, or every few nights, and then within a decade one of these things comes up, it implies that roughly once a decade or something on that scale is how often these things come from outside the solar system into the inner solar system, which is pretty gnarly, unless we got really, 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 really lucky.
So you have to be careful with the stats on that, because we could have just got lucky. So it's hard to know. But so any idea of what this thing could be?
No.
They're suggesting here neutron star, white dwarf.
I guess slow spinning neutron star, I could see it being. I don't know.
So what's giving off the flashing? Why are we not seeing this continuously? Why is it?
Well, so if it was a pulsar, the equivalent of a pulsar, but it's a slow spinning one, and so then it just sweeps around, and then you see it for a minute, and then it goes away. So it's got an 18-minute rotation period and a 1-minute window. 1 minute is so the beam of photons coming from the magnetic pole, or presumably that's where it comes from, would be 1/18 of the circumference. It would open up at an angle that's 1/18 of 360 degrees, whatever that is, 5 degrees. So you have a 5-degree opening angle, and then this thing spins around once every 20 minutes. So that's probably why they say it's a spinning thing, because otherwise what would it be, right? I guess it could be a distant intergalactic sailor with a
something
a
getting in
signal
the way.
light that like a lantern that he's opening up, kind of like the Galileo time speed of light measurement type thing. So World War II signaling.
Or something that's getting eclipsed every 18 minutes, which would be
But
weird.
it's going the wrong way, right? It's getting brighter instead of dimmer.
Oh, okay. Yeah, of course. Yeah. Makes sense.
So anyways, there we go.
Interesting. What's James Webb doing? Is that L2?
Don't know. Unfolding, something like that.
It's sat at L2, isn't it?
I think it's there now. Yeah.
It's happy. So we'll pick that one up as well.
Yeah.
But yeah, so some interesting stuff on there, and I'll probably give you. I'll probably have more of a look into this isolated black hole then, because it sounds like there might be some deeper implications, and we can chat a little bit more about that offline, especially if you're going to do a stream.
All right, let's see if there's nothing. I think we're good. I do have to run, so thank you for stopping by. It was good to talk to you again.
Yeah,
and
my pleasure.
Yeah, we'll connect again in the relatively near future.